All right, this is the first hour of Physics 1B for October 25th. And today we're going to be talking about the first law of thermodynamics. And for this, we have all these topics that are listed over here. We're going to talk about the signs of heat and work for thermodynamics, the work done during a volume change, pass between states. I don't know that any of this stuff even makes sense until we get to talking about it. But the general idea of what we want to do today is that we want to learn what the first law of thermodynamics is, and just as a hint, it has a lot to do with energy. It's very similar to the conservation of energy. We just like to apply conservation of energy basically to thermodynamic processes, which means we're going to have to talk about heat transfers and work done. So for that, we need to understand how we define heat and work in terms of their signs, positive and negative for a system. I guess we also need to understand what a system is. And then we're going to talk about how you calculate work done as a system transitions between states. And we're going to be doing that by looking at graphs of a system moving between different states and talking about how we find volumes in our curves. And then ultimately what we want to build this up to is to come up with a definition for what internal energy is, and then to actually physically state what the first law is. That'll probably be toward the end of class today. So what is internal energy? Internal energy is something that came up really early on in physics. Probably the earliest time you would have talked about this is when you were talking about conservation of energy and friction. So just as a preview is where we're going with this, long ago in Physics 1A, you probably learned that when an object is sliding along a table, right, it's eventually going to come to rest due to friction. And you could ask, well, where did the kinetic energy go? And the answer is, well, it got transformed into internal energy within the table and the object. And that's nice and all. But we'd like to be able to quantify it. We'd like to actually come up with a number for how much internal energy there is in a system. And we'd also like to kind of know what happens when the volume or the temperature or the pressure of the system changes, and then what does that do to internal energy. So that's the goal of today's class. So very theoretical stuff that we're just doing today mostly. And we will do a little bit of math, but mostly this is just a way to set up a lot of the kind of calculations we're going to be doing for the rest of the class. Okay, so let us start off with talking about what a thermodynamic system is. Okay, so what is a thermodynamic system? So this is going to be anything that we can collectively call some type of a unit. An example of a thermodynamic system, the one that your book gives is popcorn. It says you have like a vessel. This is a decently good example. And it's filled with kernels of popcorn down here. So you have like popcorn kernels. And you probably have some oil in here too. So we'll say there's some oil as well. And then, in order to make this heat up, you need some kind of a flame. And you probably cover it with a lid. Right? And so what happens, when you pop the kernels, you add heat into the system, right? So heat goes in here, Q. Q is the symbol we've been using for heat, right? That heat heats up the oil, which then, by conduction, heats up the kernels. And eventually the kernels will get hot enough that they will pop. And when they pop, they're going to expand. And the expansion of the kernels as they pop, so let's say that they've popped and now there's little tiny kernels inside of here. Kernels, these are supposed to be kernels of popcorn. I don't know how to draw a kernel of popcorn. Eventually those kernels of popcorn are going to do what? They're going to push the lid off the top, right? So the popcorn does work, W, on the lid, and it pushes it open, right? So this is an example of a thermodynamic system because it involves heat transfer, and because it's a good example because of the fact that there's energy comes in and then work comes out, basically. The work in this case is the work done on the lid by the popcorn to lift it up. That's a type of work, right? It's a force times the displacement. And there's heat coming in, okay? Other types of thermodynamic systems would be the human body is a thermodynamic system. We don't generally add heat to our body, but we tend to conservative work. What do you mean? Like as in conservative force versus non-conservative force? Is that what you're asking about? I need to turn my phone down so it doesn't give me notifications during class. I just push that button. Yeah, there we go. Will you tell me what constitutes a conservative force? Or what are some examples of a conservative force? While you're thinking about that, just other examples of thermodynamic systems. One that we're going to use a lot is the combustion engine in a car. That's a thermodynamic system. Like I said, our bodies are thermodynamic systems. What else did they say? Jet engines, airplanes, rocket engines. Anything that basically takes in heat. Okay, so gravity is a conservative force. That's correct. Other examples of conservative forces are the electric force, the spring force. That's right. And that's pretty much it. There are some others. There's like the nuclear force is a conservative force. And that's pretty much it. So Troy, to answer your question, unless it's one of those, unless it's gravity, springs, electric force, it is a non-conservative force. A non-conservative force is a force where you can't really, the work done is going to depend on the path that you take. So yeah, so it's the work done is, we don't talk about conservative work and non-conservative work. We talk about the work done by non-conservative forces or the work done by conservative forces. And the work done by conservative forces always has a potential energy associated with it. Does that make sense, Troy? So there's not really conservative work and non-conservative work. It's just work done by a conservative force, work done by a non-conservative force. Okay. This work would be done by a non-conservative force, which is the pressure created by these popcorn kernels as they push out on the system, right? Okay, so a thermodynamic system is something where you take heat in and it has the potential to do some kind of work. It may not always do work, but the work done may be zero, but it's going to take heat in and there's going to be some kind of change that's going to occur as a result of that, okay? So the first thing then to talk about is how do we define these signs? So we can say that Q is positive when heat enters the system. Like in the case above, this would be a Q is positive type of situation, right? Q is negative when heat leaves the system. So when a system cools down, the Q would be negative. I guess an example of this would be, suppose you take a pot of water and you heat it up, but then you leave it on the stove and let it cool down, then Q would be negative because heat would be leaving the system, but Q is positive when the heat goes into the system, okay? So this Q would be like negative in a cooling situation. So then the other thing is the work done. This is the part of this I think that is quite hard to understand when you're doing these problems. So this is really important. Work done is positive when the system does work on its environment. Yeah, I turned off the sound and then immediately I got a scam phone call. I don't feel like that's a coincidence. Work is positive when the system is does work on its environment. You know what? We're gonna get rid of this. I don't need my phone. Work is positive when the system does work on its environment. On its environment. On its surroundings, however you want to say that. So the work is positive in the case of the kernels because it's pushing up on the lid. The force is up. The displacement of the lid is up. So that's positive work, right? Okay, so then the opposite of this will be work is going to be negative when the surroundings or the environment does work on the system. Okay, so heat, so Q is heat, right? Just to remind you all, Q is heat, W is work. These are two of the key factors in the first law, which we will get to, but we're not saying it yet. Q is heat, W is work. Q is positive when heat enters the system, so heat coming in, that's what this picture right here shows. That when heat comes into the system, it's positive. When heat goes out of the system, it's negative. And when the system does work, it's positive. When work is done on the system, it's negative. Okay? Does that all make sense? Anyone have any questions? Pretty simple, right? Question is, can you remember all that as we're doing this stuff? And will you remember when you're doing your homework? I don't know. Just try to remember that. It's not complicated, but I promise you that you will get confused. And I'll try to help with that. All right, I don't think we need this actually today. Okay, so next thing we want to talk about, we've got the signs of heat and work in thermodynamic process. And now I want to talk about the work done during a volume change, such as this popcorn popping, for example. Although that's not the example we'll use. We're going to look at a volume change that causes a gas to expand. Again, I don't think we're going to get to this. Okay, so let's start off with just this picture right here. Okay. So in this picture right here, let me blow this up so you can actually see it a little better. We have something that's supposed to be kind of helping us understand what's happening on a microscopic level during a volume change. I do want to emphasize that while we will talk about microscopic things that are happening, everything in thermodynamics is based on macroscopic properties of the system. So I say that, what is a macroscopic property? Can you all remind me what that means? I've said it a few times now, so hopefully some of you have picked up on what I mean by this. What are some examples of macroscopic properties of systems versus microscopic? If you want to explain what a microscopic property is, you can type that down. Yeah, stuff like pressure, volume. There's a couple others, right? Big picture, that's right. Macro means big picture, micro means tiny. So there's like two more big macroscopic properties that we talk about. And we're going to add one today. What are the other ones? Just think about the big things that show up in, temperature is one, and there's one other thing. Just think about the ideal gas law. What are the four variables in the ideal gas law? Those are all the macroscopic properties. Moles in for number of moles, right? We're going to add a new one today, which is going to be internal energy. This is going to be the new one. So this is internal energy. But we haven't defined what it is yet. This is just going to be one we add today, okay? That's going to be a new one, all right? You'll notice that work and heat are not one of these things, right? Work and heat are not one of these things, but they could be. I think that the energy that comes into a system could certainly be considered a macroscopic property, and then probably the work done could as well, but these are kind of, if it's not really a property of the system, right? Property of the system or the state is pressure, volume, temperature, number of moles, and internal energy. These two are kind of about what happens to the system. And then really, all in all today, what we want to really discuss is what happens to pressure, volume, temperature, number of moles, and internal energy when we add heat to a system. And then when we add the heat to the system, based on those changes, how much work does the system do? That's really the goal of all this. And to put some kind of weight to that this allows us to answer the question, like, how does an internal combustion engine work in a car, for example? How does a heat engine in general work? How does a refrigerator work? That's really where we're going with all this stuff. Is we want to learn how engines work, and we want to learn how compressors work. We want to learn how refrigerators work, heat pumps, all these different things, and they're all going to involve all of these variables here through some type of method by which we add heat to a system. The pressure, volume, and temperature, and all these other things are going to change, and we're going to get work out of that process. And if you think about that, that's what your car does, right? Fire goes in, car moves, right? Like the gasoline in the engine blows up, and through that explosion, the car starts moving. And we want to understand kind of all steps of that process. That's the goal today. So to do that, we need to understand how work is done during a volume change and how you would calculate the work done during some type of a volume change. Because, for example, inside of a car, when the cylinders are moving up and down, there is a volume change occurring. Okay, so we look at this picture right here. So in the case of a gas, where we have little tiny molecules of the gas, right? We want to think about what happens when the gas expands, which is the first time. This is expansion. and what happens when the gas contracts. Okay. So in the first case, imagine a molecule that's moving to the right. It hits the piston, right? And the molecule exerts a force on the piston, right? As a result of this, if the piston is free to move, right, then the piston is going to move to the right. What happens to the volume of the gas then? What happens to the volume of the gas then? The volume increases, right? Okay. So this is what's happening in A right here. So this is A. The volume increases. Okay. So let's think about what happens then in terms of the work done and what happens to the energy of the system. Okay. They kind of tell you here in blue, the piston moves away during the collision and the molecule loses kinetic energy. Why would the molecule lose kinetic energy in this process? So the piston's moving this way, right? The molecule hits the piston and it bounces off. Why does the molecule lose kinetic energy? Yeah. The kind of like the reason the piston moves to the right is because the molecule hits it. Although, you could imagine a system where you're actually pulling the piston to the right and still the molecule will lose energy. But yeah, that's one way to think about it, that this molecule delivers energy to the piston, which causes it to move. Conservation of momentum tells us that after the collision, the molecule should have a smaller velocity going back in the opposite direction. That's right, okay? So the molecule loses kinetic energy, but it does positive work. Would you all agree with that statement? That the work done in case A is positive. The work done is greater than 0. Because the gas expands. And the force that the molecule exerts, right, is in this direction. The force is in this direction. And the displacement is also in the same direction, right? And when force and displacement are in the same direction, then you get positive work, right? So it tells us that when volume increases, work is positive. Pretty simple statement we can make there, right? I would think I would make that assumption, Troy. I mean, it's reasonable why you're saying that, but understand that we're going to come up with systems where that's not the case. Because physics is all about exploring all kinds of possibilities and exploiting them for our advantage, right? That's what we do with physics, right? We learn about the rules of physics and then we construct machines and devices that exploit the rules of physics and sometimes bend and not break them, but bend them for sure to our will. And we force a system to do what we want it to do. So while in the case of like the popcorn expands and it pushes the lid up, that's an obvious situation where Q is positive and W is positive as well. There's going to be other situations where Q may be positive, but a lot of that energy may go actually into the system itself in the form of internal energy, okay? Like temperature increase, right? Okay, so volume increases, W is greater than 0, that's part A. And then in B here, what's happening in B, it's kind of just the opposite. In B, for whatever reason, the piston is now moving to the left. This could be because you're pushing the piston to the left. It could be because for some reason during some type of thermodynamic process, like maybe you removed heat from the system, and as a result, the temperature went down and now the volume is decreasing. The pressure of the surroundings could have increased for some reason, or the pressure of the inside could have decreased. There's different ways in which the motion of the piston could occur, but we can think of one simple one. Suppose that we're just pushing the piston in this direction, okay? So we exert a force to the left, right? So now what we think about is what happens to these molecules now. If I have a molecule that's moving to this direction, but I push on it in this direction, would you agree that it's going to pick up energy? That seems logical, right? If the molecule's going this way and I push on it back this way with a big piston, not just that one molecule, all the molecules, but only the ones that hit it, then afterwards the molecule is going to gain energy, right? Okay, so now instead of saying the molecule exerts a force on the piston, let's just say that we push the piston to the left. Okay. And as a result, piston moves left. We push the piston to the left. Molecule gains kinetic energy, as we can see, but it does negative work on the piston. Okay. So now volume decreases. And the work done, not by us, by the way, but the work done by the gas, right? This is the work done by the gas. Or by the gas molecules, if you wish. Now the work done by the gas is going to be negative. Does that make sense? Piston goes this way. What's the direction of the force of the molecule on the piston? Does that question make sense? What's the direction of force of molecule on piston? Remember, when you talk about a force, there's always two objects. There's the force of X on Y or the force of Y on X, right? In this case, I want the force of the molecule on the piston. What's the direction in this case? Is it left or right? The force that the molecule places on the piston. What direction is it? Yeah, to the right. Just like in the first part. I can see how you might be inclined to think that it's different, but in both cases, the molecule has to exert a force to the right. Okay? And that's just because, it's like a ball, right? Throw a ball against a wall, and the ball goes toward the wall, and then it bounces back, right? Which means the force that the ball exerts on the wall is towards the wall, right? This is no different. Little molecule, which is basically just a ball, hits the thing. It bounces to the left, which means the force that it exerts is to the right. What about the displacement? Now the displacement of the piston is left, right? Because we specifically said we're moving to the left, right? So if I have displacement to the left and force to the right, that leads to work is negative, because just to remind you, force dot product with displacement is what gives you work, right? Doesn't hurt to refresh this. Which means that if I take force times the displacement and I multiply by the cosine of the angle between the two of them, I get the work. In part A, it would be F times delta X times cosine of 0. And in part B, it would be F times delta X times cosine of 180. I don't know if this is all... It's probably been a while since you did this stuff, right? But just as a reminder, this is work, basically. This is a little refresher on work. Work is positive when force and displacement are in the same direction. When they're parallel to each other, angle between force and displacement is 0. When they're anti-parallel, then the angle between the force and the displacement is 180, and cosine 180 is negative, right? So this is less than 0, and this is greater than 0. Because cosine 0 is 1. So, there we go. We now understand a little bit about the work that's done in general. We know that when the volume increases, the work is going to be positive. When the volume decreases, the work is going to be negative. Now, will that always be true? Maybe not. I don't know. But it's certainly true on these simple systems where we're only talking about work and volume changes and not talking about other possible changes that are occurring. Okay? Only these things are the things that are changing now, just volume changing. So how do we quantify it? So let's quantify the work done. No, it seems I have... This is in order. Okay. So let's quantify the work done. Okay. This bigger. Scroll down a little bit, shift these down, shift this down. Okay, so now we want to quantify the work done during a volume change. Meaning we want to create an equation. Okay. Quantify the work done during a volume change. So we have a system. Here's our system. It's this green shaded in thing here. It's going to contain some molecules. Those molecules are going to have some pressure, denoted by P. And there's going to be a piston. You're going to get used to these kind of pictures because a whole lot of what we're going to be doing for the next 2 chapters is going to be involving gases and their expansion against a piston. which is kind of what's happening inside of your automobile cars most of the time. So we have a system composed of little gas molecules. The system is just gas molecules inside of here. It could be air, it could be carbon dioxide, doesn't really matter. I guess it could be water too, but we're going to be talking about a gas. So we have a gas, and it's going to exert a pressure. It has a pressure P, and the piston has a cross-sectional area A. And so we're going to say that this gas, let's say that it's in a state where it's been compressed in the past, and now it's going to basically expand against its surroundings, okay? So the gas is allowed to expand. Which is going to lead to the piston pushing to the right. Okay, which then obviously increases the volume of the gas. And we can say that the amount of work that's done, okay, so this is going to be the amount of work that's done. We'll use the symbol dW because it's going to be like an infinitesimal amount of work. And let's think about the work that's done as the piston moves from here to here through a distance that we call dx. Then since work is force times displacement, this would be whatever the size of the force is, okay? It's not drawn in this picture here, but the force in this case, oh, it is drawn. This is the force right here. The force is this, PA, multiplied by the displacement, which is dx. But you know from your study of pressure and force that pressure is equal to force divided by area, which of course means that pressure times area is equal to force. So our force in this equation right here can be replaced with just pressure times area times dx. But then we notice something about our equation. It has something that we can probably rewrite as something else. If I take the cross-sectional area of my system, which also is the cross-sectional area of the piston, and I multiply by the displacement dx between here and here, right? What do I get? If I take A times dx, what do I get? What can we call that? That's right, you get a volume. So dx is thickness, so Troy says dx is thickness, so PA dx is going to be equal to volume, that's right. So this entire region right here, shaded in, has some volume that we're going to call dV, where dV, right, is going to represent the change in volume of the system. And again, if the little d's bother you because you're taking calculus, I mean, this bothered me when I was taking physics. These little d's would always bother me because I'd be taking calculus and immediately I start thinking about calculus. And we will be using calculus, don't get me wrong. But dV, I could have also just written this as change in volume. And we still could have written an equation here, you know what I mean? So don't get too confused by this. This little d thing, if you are getting confused. Maybe you're not, I don't know. Maybe it's just me, but I always found it really hard when in calculus I was learning about dy dx, and then I would see just dv show up, and it shows up all the time in physics, right? It's like, what does it mean, you know? Yeah, so you just have to kind of like just let it wash over you and just don't worry about it, you know? Just let it be. Understand that when I say dV, I mean just a change in volume, right? The volume increased, you know? And if this stuff is confusing to you, you can actually assign numbers to these things, right? You could say that dV, for example, could be like 1 liter, right? And you could say that the area of this was 1 meter squared and that dx was a meter or something like that. Or I don't know, that wouldn't work out. Let's see, if the area of this was 0.01 meters squared, let's put some numbers in here just to make it clear to you that these are still just numbers. Even though I'm writing them as differentials, they are still just numbers. Suppose that we let A be equal to 0.01 meters, okay? And we let dx be, area has to be measured in meters squared, right? My bad. Let's let dx be equal to 0.1 meters, okay? That's reasonable, right? Area, 0.01 meters squared, you can imagine that. That's 10 centimeters by 10 centimeters. That's what that means, right? That's what that means. Dx, if that's 0.1 meters, that means that the piston moved to the right by about a millimeter, right? Then dV would just be this times this, right? Which would be 0.001 meters cubed, which would be equal to, that's a liter, basically. That's 1 liter, as it turns out. Okay? And you can imagine what a liter is, right? Like you've bought bottles of soda or bottles of water or whatever that have a liter volume, right? It's actually a pretty big volume, right? So maybe it's not a good thing to call dV, because when we say dV, we really mean some kind of like small change. But who's to say what small is? I mean, a millimeter sure is small. This seems small, but the volume change actually is pretty big then, right? It's because the area of 0.01 meters squared is actually pretty large in reality. Oh, and you know what? That's not a millimeter. That's 10 centimeters. That's why it's so big. Anyway, okay. Does that help you all to understand that if you just remember that these are just numbers at the end of the day? I don't know. Anyway. So like I said, we can reduce, going back to our equation, work done, let's refresh. Work is force times distance. The force is pressure of the gas times the area, right? The gas is freely expanding against the piston, right? It's freely expanding. So the work done is the work by the gas in this case. No one's pulling the piston. Even though there's this arrow here, no one is pulling on the piston, right? It's just the gas that does work on the piston in this case, okay? Now you might say, well, certainly there's gas out here in the atmosphere that's doing work as well, and that's true. But we're not going to worry about that for the moment. Okay, so dW is equal to PA dx, which means that the work done is equal to P dV, okay? And then, of course, the next step is to just integrate both sides. So we replaced AdX with dV, and now the left-hand side is just going to become the work done by the gas, and the right-hand side is going to be the integral of the pressure with respect to the volume, okay? And we're going to go from because we're integrating with respect to volume, right? From whatever the initial volume was to whatever the new volume is. What would that be in this case? Well, volume 1 would be the volume here, okay? So volume 1 would represent the initial volume of the gas. We could call it V0 if you wanted to. Right? And then volume 2 is the volume after the expansion. That's all that it means. Okay? The volume after the expansion. So there's our equation. You're going to be using this equation frequently, I would say. Nice little result that work done is equal to the integral of pressure dV. And now, as long as you can write the pressure in terms of the volume, which we can, right? It's an ideal gas. We've got that equation, right? So you just take that and plop it in right there. And now you can do the integral, right? This is just the ideal gas law. I just divided by V. So that's kind of how you're going to approach these problems, and we'll do an example right here. But before we do that, I want to emphasize that this also means that if I have pressure as a function of volume, right? Like if I can plot pressure, like for example here, right? I can plot, with the ideal gas law, I can plot pressure as a function of volume, right? What would it look like? Well, it'd be something like this, right? No, I meant to switch colors, but didn't do it. It'd be something like this, right? And if I pick two different volumes, like let's say I pick a volume here and a volume here. Let's say this is V2, and let's say this is V1, right? Graphically, we can find the work done by finding this area, right? That's the work done. Because that's how an integral works, right? When I say the integral of P dV from a graphical standpoint, what I mean is the work done is the area under the curve. Is that something you all remember? Does that sound right to you all? Yeah, okay. All right. I know that you don't remember everything from calculus, but I bet you all remember that one, right? That one kind of sticks with you, right? That the work done, or the integral of a function is simply the area under the curve, right? That's a big deal. In fact, that's kind of what the whole point of calculus is, at least they tell you it is to solve that problem. One of the two problems, the other one being finding the slope at a point on a curve. Okay, so let's look at some PV diagrams. You're going to be seeing a lot of these in the future. Here's some right here. And let's talk about the work done. I think this all fits on the screen here. Let me make this as big as I can. Okay, so work done equals the area under the curve on a PV diagram. So in this picture here, we have 3 different PV diagrams, okay? We're always going from 1 to 2, all right? Let's start with the easiest one, which is this one over here. If the pressure is constant, okay, so if the pressure doesn't change, look what happens to our equation. When P is constant, right, then our work equal to pressure dV equation becomes just work. You can pull the pressure out, and then we put V1 and V2 right here. You put dV right here. And then when you do the integral, you just get pressure times the change in volume. If we were taking physics, 1B. No, we are taking physics 1B. Sorry. I don't think you even talk about this in 2A, but maybe you do. If we were in physics 2A, this is all you would do. You wouldn't be able to do this. Although you could do area under the curve. So maybe you do area under the curve in 2A. I don't know. I feel like you never actually get to that chapter in physics 2A though. All right. So remember this, because this is going to show up on problems, and there's going to be little tricky things that you're going to need to remember. But remember that if they tell you that the pressure is constant, which is going to be, by the way, start teach you some words you're going to see show up here. Constant pressure. I believe this is isobaric. Okay? Isobaric means constant pressure, okay? We'll come back to that later. I'm just introducing the word to you now because you're going to learn about, there's going to be things where it's isothermal, which is going to be constant temperature, isobaric, constant pressure, adiabatic, which I think is, I can't remember, I think it's when heat doesn't enter the system or something like that. There's one other one too that's escaping me right now. Constant volume, which I think is isochoric. They got weird names for them, but isobaric, bar for, well, that's a measure of pressure. Bar is a measure of pressure. But you can also think barometer, if it helps you remember that. The bar part of this is supposed to help you think pressure. All right, so when pressure is constant, the work done is just pressure times change in volume. That simple. Easy. This is really easy. And that would be what's happening in picture C right here. All right, let's go back to picture A. So in picture A, we have a PV diagram for a system undergoing an expansion with varying pressure, right? So the pressure is changing. In this case, the pressure at point 1 is P1, and the pressure at point 2 is P2. These represent 2 different states of the system. Remember, things like pressure, volume, temperature, they are related to the equation of state for the system, which for an ideal gas is this, right? So we say that when you move from 1 to 2, you're moving from state 1 to state 2. And you have different variables of those states, right? At point 1, your pressure is called P1 and your volume is called V1. Okay? You'll notice that the volume is smaller than it is in state 2, where you have pressure 2 and volume 2. So the volume has gone up, but the pressure has gone down. Does that seem reasonable? Is it reasonable that in a system like what we just described, where the pressure exerts a force on the piston, is it reasonable to state that in a non-infinitesimal process, so if we let this piston expand and expand and expand, is it reasonable to say that the pressure of the system goes down? Do you all agree? Yeah, give you a system, it's reasonable, right? It makes sense that the pressure is going down, right? Okay. Volume's going up. If you want to think about, if you're the kind of person that thinks about things in terms of just equations, that's fine. Then you can look at this and say, if pressure goes down, volume must have gone up, right? It's the only way that it works. Now, if I want to find the work done in this process, the work is equal to the area under the curve. It goes all the way down to here. So you find the area of this, like, kind of, not trapezoid, but it kind of looks like a trapezoid, where you've got a long line here, a short line here, and then you've got this curve that goes from here to here. So in this case, the work done is equal to the area, and the work done is positive, right? But what if we did the reverse? What if we compressed the gas? Okay, so what if we did the reverse of what we did here? And instead of letting the gas expand, we exerted our own force to compress the gas. That's what's happening here. I can scroll down and draw a picture under here. In this case, what's happening is that you've got your piston, okay? You've got your gas, right? And you're going to exert a force in this direction. And that's going to cause the system to decrease in volume, right? And as a result, the system is going to do negative work, okay? Because you're doing work on the system, technically. The system is doing negative work. And in this case, I don't know if you can see it, but there is a little arrow on this picture that's going this way, okay? And on this picture, the arrow is going this way. On this picture, the arrow is going this way. So the difference between part A and part B is that you're going from 1 to 2, which means the pressure is actually increasing, right? And when you move from this point to this point, you're going to get a negative area. Do you all agree? You can get negative area here. Area can be negative in one of two ways. One way that area can be negative is when you do an integral and you're moving from right to left instead of left to right, right? From a high value of V1 to a low value of V2. Or you can get, what's the other way you can get negative work? Or negative area, sorry. What's the other way you can get negative area? Area here is negative. Do you all understand why the area here is negative? How else can you get negative area? Just think about calculus. Not thinking about physics at all. How else do you get negative area? Yeah, if it's below the x-axis, exactly. So if I have a curve like a sine curve, right? If I find the area between here and here, when it's below the axis, you get a negative value. You don't need to always think about this, but just keep it in mind. Just keep it in mind. All right, let's do a problem. So area can be negative. You go from right to left. And it can be positive when you go left to right. All right, so let's look at the isothermal expansion of an ideal gas. Here's some more graphs, by the way. We're going to be doing a lot of these state graphs, or system graphs, what do you want to call them? Okay, so it says as an ideal gas undergoes an isothermal. So you see where these words are just going to start showing up all over the place. And it tells you now that it's constant temperature. Will you remember that? I don't know. It's thermal. When I think thermal, I think heat, but so you might think constant heat. That's not what it is. It's constant temperature, okay? They could really rename all of these, but they generally don't change things after hundreds of years. They stop renaming things. They could call this constant. They could just call it constant temperature, right? They don't need to use. I don't know. I promise you on exams, I don't know. I'm gonna promise, but probably I'll expect you to memorize what these things mean. But there's only 4 of them. It shouldn't be too hard. All right, so as an ideal gas undergoes a isothermal constant temperature expansion at temperature T, its volume changes from V1 to V2. How much work does the gas do? Okay. We pick some numbers too. Let's pick some numbers. We'll do it, but then we'll pick numbers. Let's pick 300 Kelvin for the temperature of the gas. That's pretty close to room temperature, and it's a nice round number. And let's say that the volume goes from, who knows? It doesn't really matter. Let's say that it goes from 0.0. Let's say it goes from 1 liter to 2 liters. Okay, from 1 liter to 2 liters. All right. So we'll solve it symbolically, and then we'll put some numbers on. So we learned that the work done is equal to the integral of the pressure with respect to the volume, and we have to integrate from volume 1 to volume 2. For the pressure, what we do is we replace the pressure with something in terms of volume, which in this case, it's an ideal gas, and we know that an ideal gas has the relationship that PV equals nRT, which means that the pressure is just nRT divided by the volume. So if we plug in nRT over V into here, where all the things in the numerator are constant, and the volume is changing, we get that expression there. Again, we're going from V1 to V2. I realize I left one thing out here. We need to pick a number of moles. Let's let n equal to just 1 mole, because why not? All right, so now what we want to do is to evaluate our integral. And what we can do is we can pull out the n, the r, and the t. These will all be constants. R is obviously a constant. It says it's constant temperature, so we know we can pull that out. And then number of moles. Hard to imagine how the number of moles might change in this case, assuming that we take this to be a closed system. Number of moles shouldn't change. Okay, so then we're just integrating from volume 1 to volume 2, 1 over V dV. All right, what is this equal to? The natural log of v2 over v1, that's right. The integral of 1 over v dv is natural log. Did I talk about this in this class? I can't remember if I talked about this class or it was another class, but why can't we just use the power rule here? Did we talk about that in this class? I know someone had this question. Someone thought the integral was going to be 1 over v squared or something like that. The reason why you can't use the power rule is because what we're doing is the integral of v to the negative 1 dv integral, right? What does the power rule says? The power rule says that you take, if you have the integral of x to the k dx, the power rule says you do x to the k plus 1 over k plus 1, right? If you do that in this case, you get v to the 0 divided by 0. You see the problem? This doesn't make any sense. So we have to come up with another thing for what the integral of 1 over v is, and it's natural log. It's the one power rule thing that you cannot use the power rule for. All other powers work. Even if the power was like pi, it would work. But it does not work when it is negative 1. Okay, so we get natural log. So we're going to have n r t natural log of... I'll do it in 2 steps just because why not? Not a lot of math today, so might as well go slow through it. We get that, and then as Astrolever mentioned, we can reduce this to the rules of logs. The difference of logs is a ratio, so we're going to get that the work done is equal to n r t times the natural log of v2 over v1. Okay. And then we'll have to check to see if the units make any sense, but when we plug numbers in, they will. In general, this is kind of a pretty general result for any isothermal process, right? I'm not saying you should just use that to start it. I mean, like, this doesn't take much work to do these 3 steps or whatever it takes, but, you know, you shouldn't be surprised when you get this result in your homework, if you get this log v2 or v1. All right, so then work done is going to be equal to, we said the number of moles was, does anyone have any questions while I'm writing this stuff out? Just let me know. Let's see what this is equal to. Feel free to calculate. If you get an answer, put it in the chat. $17.28. That's what I got. It's not a lot of joules, honestly, but. The cool thing about this is, suppose that we have this system, right? And we know that you get this many joules of work out of the system. About 2,000 joules out of the system. Well, what if there was a natural way to revert the system back to its original state? And then we could allow the gas to expand again so it could get back to V2 again, right? And let's say that in the process of going from V2 to V1, maybe in this process, the gas does negative 1,000 joules of work. But in the process of going from V1 to V2, it does positive 1728 joules, right? Well, then you've created a process that's cyclical where you get energy out every single time. Does that make sense? So imagine, so we just saw that all we just did was just to say that it's possible to say that if the gas expands from about 0.001 meters cubed to 0.002 meters cubed, which is basically from 1 liter up to 2 liters. Okay. It's not that big of an expansion, right? 1 liter to 2 liters. We saw that you get this amount of energy out of it. That isn't a lot of energy. 1,728 joules of energy is nothing. It's less than half of a calorie. So you couldn't survive on this many joules of energy. But imagine that we could then get the system back to the original state, right? Where it has exactly the same original pressure, exactly the same original volume, and obviously the same temperature because we've made temperature constant, right? And let's say that then doing that process, we find a way to make it basically take less work than it gave, right? If it takes less work than it gives, then you can create a cyclical process by which you repeat this process over and over and over and over and over again, and every time you do it, you get energy out, right? This is basically what happens in your car. That's why the cylinders in your car, why you have RPM, why it just keeps moving in a circle, is because you have a process that releases energy, and you have a process to get back to the original state, and then you release the energy again. You go back to the original state, release the energy again, go back to the original state, release the energy again. Now just make that happen faster, and all of a sudden the car is pumping out way more energy per second, right? That's why when you push the foot down on the pedal, the RPMs go up, right? Until it switches gears or whatever. So that's where we're going with all of this, just to keep you on track with what's happening here. We just found we're going to have to take a break, but we just found that there's a way to get work, right? There's a way to get energy out of a system when all it does is expand, right? Does that make sense? This is a really powerful idea. This is the idea that drove the Industrial Revolution, that changed the world between the 1820s and the 1860s, that led to factories being put up everywhere, that led to black smoke filling the skies. It completely changed our world and kind of sparked off the beginnings of climate change, and we're now suffering from it. But it's still important to understand where these things come from, to understand how engines work, and we're just kind of building up the pieces of that. And so for now, we just have this one piece. We can find work done when a gas expands. So we'll take a break there. We'll start again at 10:50. So we'll take a break till 10:50.